everyone. Thanks for joining, and thanks for your patience through some slight technical difficulties. Today, we have our very own Dr. Jennifer Wakulicz, who's going to present today on her work. Just a bit of information on her bio. She is a postdoctoral research fellow here at USyd, working with Don and Steph and Professor Thierry Payneau in QUT on the Introspective Robotics ARC Discovery Project. She received her Bachelor's of Science in Math and Physics from University of Sydney in 2018 and her PhD in Robotics from UTS in 2025. Her research interests are in probabilistic modeling, information theory, and planning with the objective of developing robust robotic decision-making frameworks capable of operating reliably in unstructured environments. And today she's going to be talking about her work in reduced latent belief spaces for active perception in robotics. Go ahead.
So I'll just be presenting kind of what I worked on during my PhD, and then I'll touch on like what we're bringing forward to develop introspective robotics. But basically, active perception in robotics, it's like a pervasive problem. The goal is to plan sensing locations for your robot so that it can extract information about its environment. So I'd argue that this is a really important capability to have autonomous robots that are robust to kind of changing and unstructured environments. If our robot can plan to push through leaves that occlude its vision to reconstruct apples on a trellis, it will be able to more autonomously pick the apples from the trellis. So it's not just used for this, it's used for tons of different applications. Active mapping, if you want to do bathymetry, you might want to plan a path that gives you your best reconstruction of a seabed. It can be used in robot teaming. So you might have one robot whose sole purpose is to scout out the environment for other robots. And it's also used for things like search and rescue and surveillance. So under the hood of active perception, or one of the approaches to it, is to build probabilistic states from measurements. And these are called beliefs. So here I have a robot taking a measurement of this person's, let's just say it's their X position. And I have a 1D Gaussian that represents what I believe the state to be. So the mean can represent where I think that person is. And the variance of that Gaussian kind of captures how much uncertainty I have in that state. So if you use probabilistic models to do your estimation, the cool thing is that you can reason over uncertainty and noise that comes with everything in robotics. So if you want to plan to collect informative measurements, you can plan to reduce the uncertainty in your future belief. So I'd rather take the measurement on the right because it gives me a very sharp distribution with low uncertainty about this person's state than to take the measurement on the left with a large variance and a lot of uncertainty. So planning to gather information can be formulated as planning to visit future beliefs that have low uncertainty. This is actually very difficult because belief space is very unwieldy and it's hard to explore. So it's very high dimensional. First of all, if your action space is continuous, you would have to sample actions discretely. Perhaps this is one approach. So you start with one belief, you sample some actions to see where you end up. And once you end up somewhere, you can't predict what measurement you'll take because sensors are noisy. So you have to sample possible observations to kind of predict what belief you will see at a future sensor location. So thanks to sensor noise, traversing belief space and building these trees to plan over is not a deterministic process. It involves a lot of sampling. And because of all this sampling, you can see that if I wanted to plan over some long horizon, so I have many layers that correspond to locations at future time t+1, time t+2, as that horizon grows, this tree kind of grows exponentially. So to deal with this kind of like enormity and complexity of belief space, a lot of people will try to develop really smart planning algorithms that explore just regions of belief space that are highly informative or close to optimal. In my PhD, what I did instead was to try and take kind of a kind of orthogonal approach. And instead of focusing on planning, I focused on probabilistic modeling. So if you choose the state that you're estimating wisely, so rather than thinking about a pedestrian's entire trajectory, if you think about estimating just their high-level motion, you can extract the trajectory from that variable, and the belief space associated with it is a lot smaller and more manageable. So we can use the same planning algorithms, but because our belief space is simplified and it's smaller, things are much more manageable. So again, we want to choose to estimate a variable that's related to the state of interest so that we can still recover the state of interest. And we want to choose a probabilistic model that sort of shrinks the belief space that we are trying to plan through. So I explored this paradigm for 3 kind of separate robotics tasks, and I'll give a quick overview of these today. The first is an active tracking problem, or more generally a state estimation problem for systems that are undergoing unknown dynamics. So here we would want to track this orange target. So we want to have a robot that is able to preempt the target's motion and move somewhere in the future to be able to observe it and build an estimate of its state or its position in this case. But this target is performing some unknown maneuvers. So every time one of these red X's pops up, and every time that GT/DT flashes, this target moves from having a basic linear motion model to doing something that is completely not captured by that linear motion. So it's doing some sharp acceleration and it's performing an invasive maneuver. So we need to estimate this unknown component if we want to successfully be able to track this target. So without the unknown component, the way you would do this is with the trusty Kalman filter. So the Kalman filter gives you a way of propagating beliefs over time, given future sensing locations and incoming measurements. So basically, it stores your belief as a Gaussian. So I have a Gaussian over my state. The mean is that little dot here, y hat t. And the variance is represented with the covariance matrix, kind of measures the spread of that ellipsoid, the density. And once I have this belief, I can predict what a future belief will be at a future sensing location using my linear model and something called the Kalman filter Riccati map. Basically, all you need to know is that this row mapping takes in my previous covariance and some future sensing location, and it spits out a new covariance. So here I might have 3 possible sensing locations corresponding to 3 possible future beliefs. And so the cool thing about this is that that Riccati map doesn't depend on measurements. So this problem simplifies all the way down to a deterministic one. So I don't have to sample measurements in order to predict future beliefs at future sensing locations anymore, because the Riccati map and the Kalman filter does all of that for me. So it's easier to explore this space. So once I have this unknown input in my motion model, so it's now up there in green, you might expect that I lose this property and things get much harder again. But thankfully, there's something called the unknown input filter, and some very smart people designed this. It decouples the linear state evolution from that unknown dynamics component, and it tracks an estimate of both of these components alongside each other. So completely decoupled. So I can basically use a Kalman filter to estimate the linear part of my motion, and then I can use this unknown input filter to track these evasive maneuvers. It does exactly the same thing. Again, predicting future beliefs is now separated from knowing what measurements we're going to take. So we have another Riccati map, row D, for this unknown input evolution. So if we want to do active target tracking now, we would visit beliefs in our tree that we've expanded deterministically to find one of these nodes that minimizes the joint uncertainty. So I want to minimize uncertainty in that linear component of the state, and I want to minimize uncertainty in that unknown input. This is a joint estimation problem. So even though we've determinized everything, belief space is still quite large, and choosing a location that minimizes uncertainty in the state might not necessarily minimize uncertainty in the unknown input. There's some balancing act that we have to do between prioritizing knowledge of these 2 components. So instead, we just don't do that. So the reduced belief space in this case is just to track that linear component of the state and hope that the information we collect kind of by proxy about that unknown input is enough to allow us to do tracking. But we don't just hope, we also quantify suboptimality. So this is kind of the main contribution of this work. We proved some important properties of that unknown input Riccati map. And if you have those properties, you can do some perturbation analysis, and you can just show that the optimality, so if you took the optimal path through your belief space to do the joint optimization, and if you took a path that just prioritized minimizing state uncertainty, the difference in your result scales with the distance between the optimal sensing locations to perform each task. That's kind of intuitive. But you can see just by planning in this reduced space related to the state only, we're able to do non-myopic planning in this belief space. So we have that same orange target performing the unknown maneuvers, and it's also moving through these blobs of gray, which are supposed to simulate kind of areas of greater sensor noise. So these might be clouds or foggy areas. But our robot in blue is performing long horizon planning. So it's expanding that tree for some number of time steps. And it's able to preempt the fact that this target is going to move through that cloud. And if we followed it in there, we would deteriorate our estimation quality. So it's able to do this non-myopic planning, even though the target is performing evasive maneuvers. Meanwhile, the greedy one kind of follows the target through the cloud. And this non-myopic planning still performs better than the greedy policy. So it jointly minimizes both of those two kind of possibly conflicting goals, and it gives us lower RMSE overall. So here our belief space was just to focus on the linear component of the state rather than the full state itself. But what if we want to track a target and we can't be bothered writing out the state space equation at all? And better yet, what about the fact that targets have many different futures? So it might not follow one possible linear model that we've written ahead of time. There is a lot of different modalities. You could go left, you could go right. So here's an example of that. So in each of these colors are kind of like the different possible modes that this trajectory in black could follow in the future. And if our robot wanted to choose the best place to view this target, it would have to reason over all of those future modalities. But if we knew exactly which mode the pedestrian belonged to, we can reduce our problem again. So our robot can do planning in a much easier, more efficient way. So how can we capture like the high-level motion or which mode that target belongs to? So we proposed to use homotopy classes for this. So homotopy classes are just a way of defining equivalent paths that join the same 2 points. So point A and point B, tau1 and tau2 are equivalent to each other in the homotopic sense because I can find a continuous deformation between them. So that's this dotted line in between. Meanwhile, tau3 isn't homotopically equivalent to the other two because my deformation would have to go through that blue obstacle in the middle. It's not continuous anymore. But basically, long story short, this is kind of capturing one class of paths that go to the left of this obstacle and one class of paths that go to the right of this obstacle. So it's kind of capturing, in some sense, the high-level motion of this pedestrian. And we can identify which class a path belongs to with a very sparse, discrete label called the H signature. So basically all you do is you trace rays up from your obstacles and enumerate them, and you just follow your path along. And every time it crosses one ray from left to right, you add a little +1 to your string. If it crosses obstacle 2 from left to right, you add a +2. If it goes from right to left, you add a -2. So the H signature is +1, +2, -2. You can reduce it down by canceling letters or numbers of the same value but opposite sign. So the H signature reduces to just a +1. But basically the idea is anything in your data set after this tracing process that has the H signature 1 has the same high-level motion or the same homotopy class. And anything that has a different H signature will have a different high-level motion. So we can tag all of our trajectories in our data set that we might want to learn a model, a predictive motion model from with these H signatures. And then we can predict high-level motions by simply completing a sequence. So if I observe this pedestrian crossing the first obstacle from left to right, I have a partial H signature of +1, and I can feed it through some sequence completer, like an LSTM or a variable order Markov process, and I can guess what the final H signature would be. So I've trained this LSTM on historical data, and it's going to spit out the completion for whatever I put in. The other thing we want to make sure is that our sequence completer is probabilistic, because for each possible completion of this word, the H signature, or this label, the H signature, we want to have a probability associated with it. So on the right here, you see the probability of the pedestrian not crossing the second ray is 0.52. And the probability of that pedestrian crossing the second ray is 0.48. So it's about 50-50 whether it will take one mode or another mode. So once you have this probability distribution over homotopy classes or H signatures, we call this the homotopic belief. You can inform low-level trajectory predictions. So if we train a Gaussian mixture model on all of that trajectory data, and we condition each mode according to each possible homotopy class, then we can build kind of like a hierarchical multimodal model for trajectory estimation. So now each mode corresponds to a homotopy class, and the likelihood of each mode or the weight of each mode corresponds to the probability of that homotopy class being the true one, as according to our probabilistic sequence completer. And we find that doing this makes your GMM more robust to kind of areas in your training data where you have really divergent trajectories. So here, for example, you can see pedestrians are moving either up, down, crossing straight through. There's a lot of different options. And so if you predicted with a plain GMM, that kind of chaos in your training data might confuse it. As you can see in the bottom, this green future prediction is kind of wacky. Whereas in the top, because we've observed and predicted the partial H signature and the completion of it and informed our prediction with that, it's kind of more robust to that chaos. So here, these predictions, just to note, these are made with kind of all of the trajectory information up to one point. So there's no robot that's taking sparse measurements. But if we wanted a robot to take sparse measurements, then we would have to do active target tracking or active trajectory prediction. So usually now equipped with our homotopic GMM, we would again plan in this homotopic belief space. But first of all, the kind of like traditional approach would be to visit beliefs. So visit nodes in your belief tree that maximize the information that you gain from each measurement about the metric trajectory. So what is the future xyt +1, and so on. We want to maximize information about that. For GMMs, though, this information gain doesn't really have like an analytic form. You have to estimate it. It requires kind of comparing modes pairwise. So instead, we propose to plan over the homotopic belief space. So if we just want to collect information about the pedestrian's high-level motion, rather than collect information about precisely where it's going. And this just is an evaluation of a discrete sum. So everything's really good. The other thing is, in homotopic belief space, information is really sparsely distributed. So your H signature only really changes at one of these decision points corresponding to obstacles, right? So if you're a robot and you want to collect information about the H signature, you're best off moving to an obstacle and observing the pedestrian kind of perform that split. So you have some bifurcation of possible futures, and you want to see that possible multi-mode modality collapse to one future. That's where the information gain changes. So on the right here, you see with our belief space, you get exactly that. So these blue crosses are a robot's measurements of this pedestrian walking through a shopping mall. You can see the measurements are kind of clustered around regions where the obstacles are. Whereas on the right, if you were to maximize metric information gain, your robot would just kind of follow the person along. And this is, again, evidenced if we look at heaps of these test trajectories over the whole kind of test set, and we plot the frequency that each spot in the map was visited by our robot to take a measurement. You can see that the heat map is a lot more sparse on the left, indicating that information is kind of sparsely distributed. Whereas on the right, when you're planning in metric belief space, kind of have to look at the whole map. So what happens, like from an evaluation point of view, is over a bunch of test runs, we take around, like on average, half the number of measurements with the homotopic approach compared to the metric approach. And even though we take half the measurements, our estimation accuracy is pretty competitive. So we're in blue, the metric approach is in orange. And if we look at exactly how much information is collected per measurement, you can see, so lower is better. More high-level measurement is collected per measurement. It's shown in the top panel. And we can also look at how much low-level information, so how much is each measurement providing about the metric trajectory. Also, more low-level measurement is collected. More low-level information is collected per measurement, which is kind of interesting because we weren't planning to do that. We're planning to collect high-level information. So this led us to kind of like look into the theory of it, and basically you can prove that the information gained about measurements from measurements about homotopy class is a lower bound for metric information gain. So if you maximize homotopic information gain, you kind of naturally end up maximizing metric. Cool, so here our reduced latent belief space was the belief space corresponding to homotopy classes. But we're going to switch gears a little bit, like a lot actually, and talk about environmental mapping. So in environmental mapping, you want to basically reconstruct spatial fields from measurements. So you have a little robot that's running around collecting measurements of something. It might be a vector field, so you might want to reconstruct like an ambient magnetic field or some ocean currents. It might be some terrain, so you might want to have for every XY position some depth or some height. And it might also be like for asset inspection, something like pipe wall thickness. So for every place on this pipe wall, I want some value that tells me about how thick that pipe is. But basically the goal in all of these is to take measurements of this spatial field and build a full field that has very low reconstruction error. One way to do this would be to visit literally everywhere, right? If I observe everything, then noise is my only barrier to reconstructing the field. But we can't do that. We have a finite amount of time, finite amount of energy. So what we need is to be able to interpolate the field between measurements. So to do that, you might use a Gaussian process. The Gaussian process takes observations of your spatial field, shown in white on the left, and it captures correlations between them and stores them in your kernel matrix, which is shown on the right here. So if you invert that kernel matrix, and then you multiply it by all of your observations in a vector stacked called y, then you can get an alpha vector. This alpha vector is just being filled with a projection of all of the correlations between observations and the field values themselves. So the alpha vector kind of stores like an estimate of the field value for each visited location by taking into account all of the other observations you've taken in your map. So if you want to predict the field at some unseen location x star, then you would just take a linear sum of this alpha vector weighted by the correlation between now your query point and other observation locations. So in a really reductive sense, it's just doing interpolation using field estimates that are stored in alpha. You can also predict the variance at some unseen location, but you got to note that in both of these cases, you have to invert that matrix K. And so again, if you take more measurements, the size of that K matrix grows. So if you're doing bathymetry over like kilometers, this K matrix is going to be huge. And eventually inverting it is going to become way too costly to continue. So you're going to have to do submapping and so on and so on. But an alternative approach is to use sparse Gaussian processes. So here we introduce inducing nodes, shown by the squares. And basically now our summarizing vector alpha is of fixed size. And our kernel matrix capturing correlations is also a fixed size. And I just correlate all of my observations into those inducing nodes. So now I have an estimate of the field values at those locations, fixed locations. And then if I do my projection or my interpolation, I interpolate based on these field values instead of field values everywhere that I've observed. So with a sparse Gaussian process, we can again do active perception for mapping. So things are Gaussian again, so everything is deterministically kind of propagatable. But we want to visit beliefs that minimize kind of global uncertainty in our map. So if I see somewhere that I have really uncertainty about the field value, I'd like to visit there. The trouble is evaluating this again, the complexity of evaluating this grows with the number of measurements that you take. So instead, we propose to minimize the uncertainty of just those inducing point estimates. So because we're using those inducing point estimates to reconstruct the full field, that's kind of the information that we want to be really accurate with a sparse GP. And the other good thing is everything is fixed size here. So it turns out if you do this, you kind of like respect the model that you've chosen for field estimation, and you can get richer information out of your planner. So here in the top, we're planning over the inducing point belief space. So all of these measurements are taken in order to reduce the uncertainty at the inducing nodes shown in red on the right. And you can see, because of that, the robot trajectory is shown in green. The robot kind of stays around where the inducing points are. If I have good measurements there, my field reconstruction is going to be really good. But if you plan to minimize global uncertainty, you're playing like a pure exploration game. I want to visit everywhere on my map. And so in the same amount of time, your robot is going to go off, visit somewhere really far away from where it started, and basically start collecting measurements that are less informative for those inducing point measurements. So what you find is basically exactly what I said. We collect more information faster. We reduce reconstruction error faster if we kind of respect the model that we use, and we plan to minimize error around inducing points. We also guarantee this to be true. So the error at a particular X we show can be upper bounded by something that captures goodness of inducing points. So where those inducing points are in your domain also impacts the quality of your reconstruction. But since that doesn't, once you're online and you're collecting measurements, that's kind of fixed. So all you have to do is minimize the uncertainty at inducing points, and you drive down the reconstruction error. Cool. So that's the suite of reduced belief spaces that I worked on. I'm now working on introspective robotics with Don. And so, you know, it's not clear exactly what that means. Nobody's defined it. But for me, what I'm interested in is metacognition. So building models that can reassess assumptions online based on evidence. I'm interested in kind of like Bayesian reasoning and causality. And so some of the insights that I'm taking from my PhD work into building these things are just that the models we use really dictate what's task relevant. So there we saw we were using a sparse GP, So it's better if you take measurements close to adjacent points. So you have to kind of co-design your estimation pipeline and your planning pipeline. Because if your planning ignores your model, you can end up doing kind of useless stuff or less efficient stuff. And the other thing is that having hierarchical beliefs, so having a probabilistic model for your state that has kind of a hierarchical structure, it allows you to reason over your model and assumptions. So in that trajectory prediction one, we were kind of reasoning over future high-level notions and then propagating all of that information down. So this is kind of like we can kind of extend this to kind of maybe consider some metacognitive reconsiderations kind of like more explicitly. This is kind of stuff I'm thinking about going forward. So again, introspective models that reconsider assumptions and build hypotheses and change them based on evidence, and also looking at latent spaces of autoencoders through like a belief space lens. So in some sense, that thing, that embedded space, is kind of like a belief. It stores and it uses all past measurements and kind of like observations. And so can we reason in there? Can we find structure in there to exploit? But yeah, I'm open to hear ideas. If you have ideas about what introspection is, please come and talk to me. And yeah, let's work together.
Good. Thank you so much for this great talk. We'll start with questions in the room, and then for people online, if you have any questions, just feel free to post them in the chat, and then we'll read them out loud.
Quick one. Can you go back to the slide on the environmental model, the flow field?
Yeah.
Yeah, that's right. So we're doing this at like the ocean scale.
Yeah.
And the challenge we have is we just abandoned trying to even predict ocean current models, because when our collaborator is Josh Schomburg, and when we pin him on ground truth, he gets all wiggly and it's like, no, I don't have a good answer to that because there is no ground truth.
Yeah.
And if you really think about it, like there's buoys we send out, but they're like tiny little dots in this grand ocean. And then the models that we're using to predict ocean are just kind of like guesses.
Yeah.
And so we're dealing with like, okay, we like to map and like get these models, but we just find that it's just not worth our time because it would take too long.
Yeah.
Is there, have you thought about like do you have any suggestions for how to avoid this, how to solve this problem? We're sort of at the whims of the oceans, and then we're like, I just cross our fingers and do better planning is what we've decided, but I feel like that's insufficient.
In terms of the ground truth problem, we ran into that too. We were trying to do kind of like planning in ocean currents and stuff. So we were doing like risk-aware planning. So you want to avoid really kind of turbulent areas.
We want to actually go to them because for us, it's actually, that was the part that was interesting. It's like we don't have good models there.
Yeah. And we were just doing planning, not kind of reconstruction, but yeah, definitely.
We don't even know how to get there. Half the time, there was these really interesting eddies that are formed, but these are just from the models, and we have like 3 or 4 of them from like different sources. And they're like, one says it, but the others don't say it. So what we want to do is like send that glider there, and these are things evolving over like big, huge structures, evolving over like months.
Yeah.
And so the problem is, how do we make sure that that little robot stays in that spot for as long as possible, and then collect as this goes back to collect as little data as possible, because we don't get that much data.
Yeah. I think you could. So basically, as is kind of the point of all of this, choosing your state correctly,
that's
can
maybe
encourage. And we were talking about ergodic searches earlier.
That's how we're getting around this. We're just saying,
if you're informative hotspot, then most of its time will be spent there.
Yeah, the issue is getting the heat map is what we found as a hard problem. It's like we can send there and we can send you ergodic, and it'll do just like the worst case motion, and it'll get me data.
Yeah.
But then is that I could just do uniform search and it'll work, but that just seems ridiculous. I feel like I can maybe be better about my choices of the model. I just don't have a good understanding of maybe the GP structure would be good, but that feels like it's so big.
Yeah. The ocean's big for a GP.
I know, exactly. That's what we're like. We crossed it off the list. We're like, does it work?
Take it in there.
And these models are
in terms of the models, I think one thing we found useful was to use the historical.
Okay.
And historical forecasts. So they have ensemble forecasts.
Yes, those are the ones we're using.
Yeah.
And we
Those
take
are
the
really
discrepancy,
good.
but that's like so like 7 gigs worth of like,
Yeah.
and I had to plan in that. So it was like, that just seems like not a good use of our time.
We ended up, just to demonstrate our planner working in a bunch of different weather types, we ended up selecting specific forecasts from the ensemble.
And just using
And
it as
just
like
being like, this is interesting playground. Let's plan it.
That's what we basically did.
Yeah.
Or we're like, this is maybe the only option we have.
Yeah.
It just feels unsatisfying though.
Yeah, definitely. I think we talked to some Bond people, and they were also very like, well, this isn't ground truth. Like every time we said, oh, we'll use this as ground truth.
They're like,
No,
it's
no.
not.
Yeah, don't do that.
All right, thanks.
Just about the introspection, I think you have a slide towards the end where you were sort of, yeah, this one.
Yeah.
So this first line could also, depending on how you interpret it, describe just machine learning or reinforcement, where you could say the model's assumptions are kind of the parameters in the model or perhaps hyperparameters, and based on growing evidence, we'll adjust those parameters.
Yeah.
So how, for your sort of, is there a distinction where something becomes introspective robotics as opposed to kind of learning-based robotics? Or?
I think the stuff that I'm thinking about, there's an explicit loop. So there's some signal about some growing like kind of satisfaction with the current model parameters. So it might be the log likelihood of the data or something like that.
Mm-hmm.
And at some certain point, that should trigger some sort of like discrete planning action that changes everything. So whether it's like a reoptimization or such. Whereas I think reinforcement learning is kind of like over time. It takes a while I guess it's the difference between fusion and something a bit more discrete than fusion, where it's like, I'm going to rewrite history.
It sounds a little bit like sort of adaptive control of based reinforcement learning, where you're, over time, you're observing the model's predictions and updating the predicted model and then using that in some sense.
Yeah, I think the other thing about separating into hierarchical structures is if one of those layers is about like a state that has to do with the model itself, so maybe it's parameters, possibly you could do active perception for just figuring that out.
Okay.
So you have some kind of explore and exploit, where it's like, I'm exploiting my model, I'm exploring, but now I know that I should actually take measurements to disambiguate that layer, like the model assumptions. Yeah.
And I guess you could do that like at each level where you're varying some assumptions. There's also some assumptions like that.
Yeah. Yeah.
Oh, yeah, another very minor technical question. The H parameter that I want to talk to you classes, is it the sequence of numbers, or you just add them all up at the end? It's
the sequence. Yeah. So it's the label. The thing about adding them was just if you wanted to reduce it to an even more sparse label.
Oh,
so
okay.
if your trajectory double crossed,
yeah,
that's equivalent to just like never crossing.
Yeah.
And so you could capture that by doing that reduction.
Is this in any way related to like path signatures? Which is like a
yeah, path signatures is so cool. This is, I would say this is like the discrete maybe version.
Gotcha.
Right? Because path signatures are like nested integrals.
Yeah, but we eventually make them discrete anyway.
Yeah.
At the end of the day.
One of them kind of like the first layer captures like kind of curve.
Yeah, exactly.
Yeah.
So you could like finding this complex analysis. So
Which I think-
around the singularity.
Yeah. This is, so if you looped your H signature, one, which is something that reviewers were like, what if the pedestrian loops?
Yeah.
It's like, go ahead, do my best, go to a shopping mall and
but embedding that in the signature theory would just solve. I mean, that is what you're kind of doing, right?
so it would blow up the space like of H signatures. So it's not ideal, but yeah.
You can compute distances in there, and that's actually okay. You're right, you're capturing the probability of monstrosity, because it's like a big, huge, like
a lot of
tensor.
options. Yeah.
Yeah, then that's not worth doing.
Yeah.
Well, so it's just like this, you're using this for tracking pedestrians, but you could also consider this for like a topological planning, right? If you just want to plan a path through
Yeah.
a
Yeah.
single field, you're just kind of choosing which
Yeah.
which sequence of left or right.
Yeah, so people already do that. So you have some notion of optimality for each path, but also there's an optimal path that goes left around something and an optimal path that goes right. So you have a single optimal path in each equivalence class, basically. Yeah. And then you can pick from whichever you like.
Can I? With that, when you were, so here you're showing that like you've defined each of the obstacles, you're trying to define the race, and then you're calculating. For when you were extending it to the shopping mall data, were you also manually like kind of defining all the intersections or obstacles? Is that, or is that something that?
Yeah, so the ray crossings, we calculate the ray crossings just with like a cross product.
Okay, but like that's, I guess, my question. So it's like in that you were kind of specifying what the obstacles are in the
Yeah,
space.
yeah. You have to know.
You have to know that.
Yeah.
Okay.
So really cool work. So in the 2D case, you can use a counter, by sketching a line. Thinking about the high dimensional case, because like even in 3D, there's only like like inside a donut and outside of a donut.
Yeah.
Would there be some way of setting up a counter? I was thinking of manipulators and
Yeah.
yeah.
I also wanted to extend this to 3D and then I gave up.
This is what bothers me with the
But-
signatures. It's also like possibly hard because the signature pattern just like blew up
Yeah.
exponentially.
And there's just, I couldn't think of anything as simple as a ray crossing.
I see.
There's some you can integrate across your line.
Yep.
Basically, you do some complex analysis. So holes in your space, we integrate like winding numbers and things like that.
Yep.
That can give you H signatures in 3D. But it's like not as efficient and easy as just a ray crossing.
Thanks.
So if you thought about that in a learning context, instead of trying to hand engineer the signatures, the ultimate goal is to project on some lower dimensional manifold of characteristic behaviors. Could you learn those characteristic behaviors instead of hand engineering them?
So like I'd argue in some sense, this plain GMM is trying to do that. Right? I'm giving my model the option of learning different modes, and it's performs worse than explicitly telling it. These are your high-level motions.
Dissatisfying. It feels like there should be a better way to learn the.
Yeah, I mean, you could always
structure.
also not use the GMM, which is kind of
On that thought, Don, I have a Coral 2019 paper about kernels over trajectories. So you can.
Are you familiar with the work of William?
Question.
So you can have inducing points over like representative trajectories actually, and
Oh yeah, like having a GP to represent a trajectory, and then having inducing points. For
spatial trajectories.
Yeah. Because it's just interpolation, as I said.
Yeah.
It's the ray crossing thing actually reminds me of it's maybe 10 years ago or something, or even longer, 10 years ago. Steve Laval, after he did the RT stuff, he started working on like weird discrete state estimation problems of like how do you place laser beams in an art gallery so that if somebody's going through corridors, they have to cross at least one of them. Sorry?
When he pitched for Goodicity that.
Oh, was it?
Yeah.
Did you look at that, any of that stuff? I mean, it's kind of
Yeah,
like
I did. So
some
the
of
first
it.
draft of everything was like, because that was all posed as like minimalism in
Yeah.
like, what's the minimal
It's
sensor
very
to
abstract.
do it?
Yeah.
I was kind of like, I'm gonna go with that. And then I was kind of like, this doesn't super fit everything that I'm doing. Yeah. But I've seen that and that's really cool. Yeah.
I have a bit of a new question about the last part with field reconstruction. This field that you're reconstructing, are there any assumptions, limitations about it? Because I noticed that it's a bit of a linear operation. So if there's like something abrupt in the field, will it handle that, or will it smoothen it out?
Yeah. So GPs, your smoothness of your reconstruction is dictated by that K. So there's functions that capture correlation. you can say the correlation is really high at a particular length scale. And so you kind of define how far data is correlated, and that corresponds to smoothness. So if I say my correlations are really short, I get lots of wiggles. If I say my correlations are really long, I get kind of lower frequency wiggles. It also depends on what function you use itself. So some of those kernel functions are smoother than others. But in general, if you have an actual discontinuity, I think your GP will most likely smoother. And that's why that's like what I'm doing now, right? I'm trying to like cut those correlations in my model. Yeah.
Yeah, so basically, not only provides us the uncertainty, but also the Gaussian kind of the geometry of the space. Okay, got it.
Very similar question, I guess. So there was talk of like goodness of inducing points. What does that mean?
So because I'm building estimates at all of my inducing points, and I'm using those estimates to reconstruct the full field. And I'm being very reductive when I say it's interpolation. So I'm taking the field values at those inducing points, and I'm just writing it out as a linear sum of like correlation multiplied by those field values. But if you look at a GP through this kind of reductive lens, you can access all of interpolation theory. And in interpolation theory, there's a lot to do with where your interpolating points are placed and how that impacts your reconstruction error. So that's what this is capturing. So I place them on a uniform grid, and for somebody going in blind, that's the optimal choice. You want coverage, but if you already had data, you might want them denser, where data is more varying, like high frequency varying, and less where it's smoother. But that's what this captures.
And do you need to place them all at once in your setup?
So in this, I don't touch the inducing points, but you could have a recursive loop. So I'm going to build my field, and then I'm going to optimize where my inducing points are based on the data I've collected. And then I'm going to keep collecting data, and then I'm going to optimize where my inducing points are. But the optimization of the inducing point locations requires like a pretty slow optimization. Yeah.
Any other questions? Any questions online? If not, let's go ahead and thank our speaker again.